All right, while you are making your way to myOpenMath, or sorry, not myOpenMath, to the ZipGrade student portal, I want to make a note about a few questions that are not really covered in your quiz, but that are kind of covered on your test. And these are some questions from the myOpenMath assignments. 705, that review that we did the other day. Take a look at number 5. On that, in addition to the quiz that we're about to go over. And of course, all the questions on there are good, but a lot of them are already covered on the quiz, so I didn't list all of them. And then 702.3, specifically numbers 14, 16, and 17 would also be good questions to look at because, again, they're not really assessed on the quiz very well, or maybe not at all in some of those cases, but there are some questions on the test that are kind of similar. So in addition to today's quiz, please also look back over this as you are preparing for your test tomorrow. And then, of course, you have a unit summary with a lot of practice problems as well, and you can go back through the myOpenMath stuff and work on it again. Those are pretty good assignments to help get you ready for it, especially 702.3 because that's mixed practice. It's got kind of everything in there in the review because those are both pretty cumulative. So those are good things to look at in addition to today's quiz. But back to today's quiz, which hopefully you've had a chance to get opened up on your own screen. I am looking at Form A. If you had Form A, you're going to be going along in the same order that I am. But if you had a different form, you might need to skip around. And again, if you have that PDF opened, you're looking, at least for the first part, for this diagram. If it doesn't happen to be on page 1 for you, just go to the next page and see if you can find it. But the question says, use the information and image below to answer the next 3 questions. The diagram below shows labeled points on the trajectory of a projectile thrown forward at an angle. Assume points that appear to be at equal height are at equal height. Okay, so they're just telling us that since there's not like a grid or something, that we're going to assume C and E are at the same height, B and F are at the same height, A and G are at the same height. They appear to be, so we're going to assume that they are. Okay, let's go ahead and take a look at number 1. Number 1, nobody missed. Every single person got this question right, at least in my classes. And it says, which point has the lowest magnitude of velocity? Okay, and so basically asking you, hey, where is this thing moving the slowest? And if you look at this, you know that as you throw something up in the air, even if you throw it forward up in the air, which is the case here, that it's going to slow down as it rises, and when it reaches max height, which for this is at point D, it will have a vertical velocity of 0. Not a total velocity. If you throw it forward, it's still moving forward, okay? But its vertical component will be 0. But since the forward component's the same everywhere, if the vertical one's changing, then that's really going to determine where you have the greatest speed and the slowest speed is going to be kind of based on that. And so the answer to number 1 should be D. You would have the lowest magnitude of velocity at that point because you wouldn't have any vertical velocity. You would just have the horizontal component there. And so number 1 should be D. Number 2, y'all didn't do as good on. Okay, I'm not sure why there's such a difference between them. Not that it was terrible, but like 75% of you got number 2 right. Well, at least as a campus. I didn't actually look at this class period, so let me check that. It's about the same. Okay, and it says, which point has the greatest speed? And so if you look at this, my speeds here, again, my slowest is still D. Okay, but if I want to talk about where it's moving fastest, your projectiles will be moving fastest immediately after they're launched, which would be at point A, and immediately before they land, which would be at point G. And because A and G are at the same height, they would have the same speed. Okay, one's up, one's down, but they would have the same speed. Okay, and so the greatest speed would be A or G. Only one of those is an answer, though. And so the answer you're going to select for number 2 is A, because that's the only one available to you out of those choices. If A and G were both there, you would have to pick both of them. Okay, because they would have equal speeds at those 2 points. But again, from A to B, it's going to slow down, and then it's going to keep slowing down until it reaches D, and then it's going to start speeding up, and it'll get faster, and it'll be fastest at G. Are there any questions about numbers 1 or 2 before I move on to number 3? Okay, so number 3, 75% of you guys got that right in this class, but it says, which of the following statements is true about this projectile launched at an angle? And this was a problem because some people, when they read this, thought that there was more than one answer, but it's not written as if there is. It says which of the following statements is true, not which are true. So hopefully you only picked one thing, because if you picked more than one answer, automatically you're going to get it wrong. There's only one correct answer here. Okay, and I also said that in class for anybody who asked. If we read these statements, A says the velocity at points C and E is equal. C and E are at the same height, and so we would have the same speed. But velocity is a vector. It's not just the magnitude, it's not just the number, but also the direction. And very obviously they have different directions. Maybe one of these is 10 meters per second up and the other is 10 meters per second down. Okay, they would not have the same velocity. If this statement had said the speeds are equal, then you could have picked it. But because it says the velocities are equal, that is not true because the directions are not the same. One's up, one's down. Okay, so we cannot pick option A. Option B says the velocity at point D is 0. And again, I addressed this a second ago as well. The vertical velocity at point D is 0. But this projectile was thrown forward at an angle, which means there is still forward velocity at point D, and thus its velocity isn't 0. Not its total velocity anyway, just its vertical velocity. And so we do not want to pick answer choice B. Answer choice C says the vertical acceleration changes. Guys, if I throw something up in the air, if we launch a projectile, why does it slow down as it rises? Gravity, right? The only force acting on our projectile is gravity. That's the acceleration. That's what accounts for the acceleration. Does gravity change? No. It's a constant negative 9.8 meters per second squared. So our acceleration isn't changing. It's constant. Our velocity is changing, but that's not what this says. This says acceleration is changing, and that is not a true statement, so we cannot pick answer choice C. Answer choice D says the horizontal component of the velocity is constant. That is your answer. That's always true. We've been writing it in this table the whole time. Every time we do math, we write in acceleration horizontally is 0, and we put the same number for the velocity for VI and VF. Because there is no force in the horizontal direction, you will have constant velocity horizontally, and that is the choice that you want to pick as D. Let's talk about E, though, just to make sure we're good. It says the time from point A to D is greater than the time from point D to G, and that's not going to be true because this is time up and time down. We're going from the same height and then back down to the same height that we started, and so those times should be equal. Okay, so it's not going to be greater on one side than the other. Time up equals time down. The only acceptable answer to number 3 is answer choice D. Does anybody have a question about numbers 1, 2, or 3? Okay, then let's go ahead and move on to number 4, which looks like this. Okay, so again, if you have a form other than Form A, please find this picture. It says, the diagram below represents the path of a stunt car that the fall guy drives off a cliff, neglecting friction. Compared to the horizontal component of the car's velocity at point A, the horizontal component of the car's velocity at point B is blank. And you're here, just need to tell me that it's equal. We just talked about this in the previous question. The horizontal component is the same everywhere because horizontal acceleration is 0. So A and B have the same horizontal velocity, but so does every point in between them. And so does every other point on that trajectory. So long as you are in free fall, your horizontal velocity remains constant. The answer to number 4 should be A. And let's see how you guys did. Yeah, only one person missed that in this class. So you guys did really good with number 4. All right. Questions about this one? Let's go ahead then and take a look at number 5. Again, on Form A, number 5 is this one about a cannonball being launched horizontally with a velocity of Vx. Again, if you do not have Form A, please look for this question. 80% of you got this question right. So again, not the best, not the worst. But let's go ahead and talk about the answer and why it is that answer. It says, a cannonball launched horizontally with a velocity of Vx will hit the ground blank as the same cannonball launched horizontally at the same height with a velocity of 2Vx. In other words, if I double the velocity of my projectile, how does it affect the time that it takes to hit the ground? That's what this question is asking. Okay, because it's saying we're doubling this, but we're leaving the height the same. And it's the same cannonball. So the only thing we're changing is the launch speed, but it's a horizontal launch. Okay, and you need to remember this. Horizontal motion is independent of vertical motion. We've talked about this, I don't know how many times now, but we looked at it in the FET. I showed you a video of the Mythbusters, like firing a bullet and dropping one from the same height. That horizontal speed has no effect whatsoever on the airtime. Okay, it's just dependent upon the height that it's launched from, if they're both horizontal. Okay, now if it's launched at an angle, that's different. Okay, but if they're both horizontal, then it really is just going to depend upon the height from which they are launched. Okay, so the speed doesn't matter. The answer to this for number 5 should be at the same time, which is answer choice C. Okay, let's go ahead and, before I do that, does anybody have a question about number 5? Okay. Number 6 and 7 both go with this scenario. It says, a model rocket flies horizontally off the edge of a 100-meter high cliff at a velocity of 50 meters per second and lands on level ground below. Sketch a picture of this scenario on your own paper. So, let's go ahead and draw a picture of what's happening with this launch. I know that I have my model rocket. I know that my model rocket is flying horizontally off the edge of this cliff with an initial speed of 50 meters per second, and that this cliff that it's on is 100 meters high. Okay, I know that when it does this, it's going to become a projectile and it's going to follow a trajectory like this, and it's going to land somewhere over here. And that's what the first question is asking, is how far away does it land from the edge of this cliff? So in other words, what is the horizontal range? What is delta x? That's what we're trying to find. Okay, so let's go ahead, and if we're trying to solve for this, we really need to start by labeling some information. And I do want to keep my horizontal and vertical data separate, so I'm going to make myself a little table to keep horizontal and vertical data separate. And I'm going to be labeling those variables we've been looking at this unit that we use in those kinematic equations, VF, VI, A, T, and delta X or delta Y. Okay, so if I take a look at this, I know my horizontal velocity is 50 meters per second, and that's my initial, I wrote this in a weird order for some reason, but that's my initial launch velocity, but it's also my final velocity because horizontally my acceleration is 0. Okay, again, this is always true. Horizontally, these will always be equal to each other. Okay, vertically speaking, because I have a horizontal launch, and this is always the case, if you have something launched horizontally, that means it's not launched vertically. So my initial vertical velocity will be 0. Okay, so my VI vertically will be 0. My acceleration vertically will be due to gravity, which is negative 9.8 meters per second squared. I know it's going to speed up. I know it will have some final velocity vertically. I just don't know what it is. Okay, and I know how far it's going to fall. 100 meters. That's how high the cliff is. That's also how far it will fall, making my vertical displacement negative 100. So from this information, again, ultimately I'm trying to find my horizontal range, this value right here. But in order for me to find that, I have to get time. I have to find time. And I need to use my vertical data to do that. So we're going to find time using my vertical data, and then we're going to find range once we have the time. And we have the velocity over here, we'll be able to find delta x. So looking at the vertical side of this, I have VI, A, delta x, I'm looking for t. The equation that we're going to use is this one. Delta y equals VIT plus 1/2 AT squared, because that's the information we have. if we substitute into this equation, I'm just going to move this up so we can see it. If we substitute in here, this will be negative 100 equals VI is 0. Therefore, VI times T will be 0. That whole thing's going to go away. 0 plus something I don't need to write. So I'm not going to bother writing it. I'm just going to write this. 1/2 times negative 9.8 times T squared. So this will be negative 100 equals negative 4.9 T squared. And then to get T by itself, we're going to divide both sides by negative 4.9. Those negative signs are going to cancel. 100 divided by 4.9 is 20.41. But that, again, that's equal to T squared. So we need to take the square root of it. And that gives us this for our time, 4.52 if we round that. All right, so now that we have our time, we can find our range. Again, this is not our answer. We're not done. We have to solve for range still. Okay, now horizontal range or horizontal motion in general is constant velocity motion. I don't have any acceleration. And if I have constant velocity, the kinematic equation I should be using is the last one. This one right here, I think it says VI plus VF, but whatever. Doesn't matter which order you add them in. Basically, it's average velocity, that's this right here, times time. And since my velocities are the same, 50 plus 50 divided by 2 is, of course, 50. So if you have constant velocity, you can write it like this. Just velocity times time. Okay, you could also use the this equation here, because if you put a 0 in for A, you're going to have delta x equals velocity times time as well. Same thing. But we just need to multiply the time that we just found, this 4.517 number, times that velocity, velocity times time, so times 50. And this is my range, 225.87. I think the answer here is rounded wrong. It's 225 instead of 226, but it's the only one even close. And so you should have selected answer choice B for number 6. Questions about number 6? Okay. Then let's go ahead and take a look at number 7. All right. Number 7 was one of the most missed questions. In this class, it was the most missed question. So let's talk about what the answer is and why. By the way, number 6 y'all did great on, only one person missed it. But number 7 says, if the model rocket has a mass of 0.75 kilograms, what is the work done by gravity on the rocket during its free fall to the ground below? Okay, guys, this object, this rocket, when it's in free fall, so pick any point, it doesn't matter, but when it's in free fall, the only force acting on it is gravity. Fg, that's it. Okay, so that's the only force to consider. There are 2 ways for me to solve for work. One of them is to find the initial kinetic energy, the final kinetic energy, and to subtract. But that's going to be harder because if I wanted to do that, I would have to figure out what this diagonal velocity is when it impacts the ground, and I don't want to have to mess with all that. The easier way to solve for work in this problem is to multiply force times displacement. Well, the force acting on this object is Fg, and the displacement of this object vertically, because again, when we talked about work, all I care about is the displacement that's parallel to my force. My force is down, so I only care about vertical displacement. I don't care how far sideways it goes. My vertical displacement is, of course, delta y. So that's how you're going to find work, Fg times delta y. Now, I don't have Fg. Fg is the weight of this model rocket. However, they did give me the mass, and I know that Fg is equal to mass times gravity. And so the mass in the question is 0.75 kilograms. So I'm just going to take my calculator and I'm going to multiply 0.75 times negative 9.8 because that would be my mass times gravitational acceleration. Yeah, that gives me a weight of negative 7.35, and it should be negative. It's downward. So we're going to say that Fg is negative 7.35. And then we're going to multiply it by the vertical displacement. Well, my vertical displacement, I already wrote it right here. It's negative 100. I'm falling by negative 100. When I multiply negative 7.35 times negative 100, I get positive 735 joules. The answer is C. Those of you who missed it overwhelmingly put B, which means you got the right number, you just have the wrong sign. Guys, we've talked about this previously, but I'm going to remind you real quick. Your work will be negative if the direction of your force is opposite the direction of your displacement. Or you can think about it in terms of energy. If it's losing energy, then the work is negative. But this isn't losing energy, it's speeding up as it falls. It's gaining energy. That should be positive work. Or look at it in terms of the direction. My force is down. My displacement is down. They're in the same direction. Mathematically speaking, if I multiply a negative times a negative, I get a positive number. My work here should be positive, both because of this and because I'm adding energy to the rocket. It's getting faster. Okay, so again, the answer to number 7 should be C. Now, just to clarify, gravity can do negative work. If I throw this highlighter up in the air, it will slow down until it reaches the maximum height. That's negative work. As it rises, it will slow down. And it's negative work because it's losing energy, it's slowing down. It's also negative work because the direction of displacement is up and the force is down. If they're in opposite directions, you're going to get a negative work. Okay? Or again, think of it in terms of energy. But some of you had trouble with that one just with the sign, although there were some people who put A also, I think. Yeah. But the most common wrong answer was B. Questions about number 7. Again, if you need to make a note about the sign of the work that's happening, make a note. Okay? Because gravity can do negative work if it's working against the motion of the object, if it's going up. Okay, but if the object's going down, your gravity will be doing positive work on the object because it's going to make it speed up. All right. Next questions go along with this scenario about cannon A and cannon B. And this is questions 8 and 9 on Form A. It says, cannon A is aimed at an angle of 25 degrees. Cannon B is aimed at an angle of 65 degrees. They are fired with the same muzzle velocity and launch identical cannonballs over level ground. Okay, so just real quick, before we answer these questions, I'm going to draw a picture because if we have, let's say this is 90 degrees, okay, then cannon A is being launched at kind of a shallow angle like this, whereas cannon B, and again this is 25 degrees, whereas cannon B is being launched at a much steeper angle that looks something like this. Again, it's probably not to scale, but you get the idea. And this angle right here, it says is 65 degrees. Okay, so you need to be able to visualize these angles because that should also help you answer it. Okay, but it wants to know which would have greater air time. And if you look at these, you're going to have more air time if the cannonball reaches a greater height because it's going to take it longer to get up there and then longer to fall back down. And obviously you're going to get a greater height with something like this that is more vertical. Cannon B is launching this cannonball more vertically. And so this one's going to go pretty high. Okay, before it comes back down. This one's not going to go very high. It's not going to be off the ground for as long, and therefore it's going to have less air time. Okay, and so question 8 says, although both cannonballs have the same range, why does cannonball B have greater air time? And I was nice and I told you, hey, these have the same range, which they do. Okay, we talked about that previously as well. If you don't remember, I told you that you get the greatest range at 45 degrees. That's the greatest range that you can get. But if you are equidistant, if you're the same number of degrees away from 45, which these are, 65 is 20 degrees larger than 45, 25 is 20 degrees smaller than 45, they're the same distance away, you're going to get the same range. Okay, but that doesn't mean you get the same air time. So let's look at the answer choices. I'm going to redraw these real quick. So A is going to look something like this, whereas B is going to look something like this. Okay, and you have components of these. That's why I'm redrawing them, because these questions are referring to these components. They're not to scale, so just go with me here. But it says, why does cannonball B this one, have greater airtime. And your first option is initial vertical velocity is greater. So that's this component. And it absolutely is greater because it's a more vertical angle. You're going to have a greater component in the y direction. So statement A is true. Statement B is not. These both can't be true. Initial horizontal velocity is greater. No, it's not. This is smaller. This is much more horizontal. Okay, but this, having a larger horizontal component doesn't give you more airtime. It's the vertical component that does. So A is your answer. Okay, initial vertical velocity is greater. That is true for this one. This is greater. That's going to cause it to go up for a greater amount of time. It's going to go up to a higher height, and then it's going to be up higher. It's going to take it longer to fall back down. Yes?
So then what velocity weren't they launched at? You said they were launched at the same time.
I'm sorry? They're launched with the same muzzle velocity. That's referring to this initial velocity here. So let's say they're both launched at 100.
What's a muzzle?
The cannon. It's your launch velocity. So they have the same launch velocity. Both of them are, let's say, 100. It doesn't say what it is. Okay, but they're at different angles. This one is only at 25 degrees. This one is at 65 degrees. So it's asking you to look at the components of that initial launch velocity.
But you just said they're the same.
The launch velocity is the same. The components aren't the same.
Oh, okay.
Any other questions? No? Okay, so again, 8 should be A. This has a greater vertical velocity. That's going to make it go higher. Okay, and there, if it goes higher, it's in the air longer. Number 9. Number 9 says, assuming the launch velocity is kept constant, which change to cannon A would result in the cannonball traveling a greater range? So the first two options are about the mass of the cannonball. Okay, it could be more massive or less massive, but it's about the mass. Okay, and we've talked about this a few times now, but again, if you need to make a note of it, make a note. Mass does not affect your trajectory. It doesn't affect your range. It doesn't affect your airtime. It doesn't affect anything. Okay, if there's no air resistance, which is our assumption when we're talking about projectiles, okay, if there's no air resistance, then mass has no effect whatsoever on free fall either. We've looked at this multiple times. If I dropped a bowling ball and a marble, they'd hit the ground at the same time. Okay, so the mass doesn't have an effect, which means it can't be A and it can't be B, which means it also can't be D and it can't be E. So the answer has to be C by process of elimination. Fire the cannonball at 45 degrees instead. And yes, that is the greatest range you will get is at 45 degrees. So that would be the only answer here would be C. That's not the only thing that could affect range though. It's just the only choice I have in this question. There are other things that could affect the range of your cannonball. If there was an option that said, hey, elevate the cannon so it's off the ground higher, yeah, you're going to get greater range then. If it had said, launch it on the moon instead, reduce gravity, yeah, you're going to get greater range then, because if you have less gravity, it's going to take it longer to slow down when it goes up, which means it's going to go higher. And then it's going to take it longer to get back down to the ground, which means you're in the air for a longer amount of time, and therefore you're going to go forward longer. Okay, there are other factors that could affect your range, but the only one here that we can choose is C. Are there any questions about numbers 8 or 9? Okay. All right, so I think y'all did, if I recall, okay on those. Yeah, most of y'all did, although number 8 some of you had some trouble with. Okay, only about 60% of you got number 8 right. 9 was better at 75%. All right, let's talk about number 10. Okay, number 10 is a calculation, but it's also a scenario that you really need to understand some of the conceptual stuff that we talked about in order to answer it. It's about Gomer. If you're looking through your quiz, look for the question about Gomer driving east. Okay, and it says, Gomer is driving east at a constant speed along the road when he drops a piece of gum from his driver's side window that is 1.8 meters above the level road below. If the gum lands 13.3 meters east of its drop point, how fast must Gomer be driving? Before we can really answer this question, again, we need to understand conceptually a couple of things about this scenario. We've talked about this scenario before. I gave you guys a warm-up question about Mario dropping a banana peel from his cart. We also saw a question about a plane dropping a package as it flew. And the thing you need to keep in mind is if you're holding something like a piece of gum or a banana peel or anything while you're in a moving vehicle, whether it's a car or a plane, okay, then that gum or that banana peel is moving the same speed you are. And when you drop it, when it lands, you will be right next to it or right above it in the case of a plane. Okay, but you'll have the same horizontal position as it does. Because as the gum is falling to the ground, it's a horizontal projectile, okay, because it had an initial horizontal speed. You drop it, it's a horizontal projectile, it falls to the ground. If there's no air resistance, it's going to keep moving forward at the same speed that the car is. So when it lands, the car should be right above it or right next to it, whatever, however you want to think about it. And so you need to keep that in mind. Because when the question says that the gum lands 13.3 meters east of its drop point, how fast must he be driving? Okay, if we solve for the initial velocity of the gum, that's also his initial velocity because he was holding it, okay, but whenever he dropped it. So if we keep that in mind, now we can set up a calculation to actually solve for this. So I need to set up a table, and I'm going to keep separate my x and my y data. And we're going to be looking for initial velocity, final velocity, acceleration, time, and displacement. All right, in this question, I know that the driver's side window is 1.8 meters above the ground, meaning that it will fall 1.8 meters, because again, this is basically a horizontal projectile. It's going to fall to the ground below, and it's falling from this height of 1.8 meters. So that's going to make this negative 1.8. Okay, I know that the gum lands 13.3 meters east of its drop point. So I know how far away it lands from where it was dropped. That's my range. My horizontal range is 13.3 meters. Okay, that's the only information that I appear to have, but I do know some other things to be true. I know that if I drop something out of a moving car or a moving plane or whatever, that I didn't give it any initial vertical velocity. I know its velocity is horizontal, meaning its initial vertical has to be 0. Anytime you have a horizontal launch, your initial vertical velocity will be 0. So I know that. I also know that my accelerations, vertically it's due to gravity, negative 9.8. Horizontally it's 0. I can fill those in. And from here, I now have enough information to start to solve. I'm looking for how fast he's driving. I'm looking for this, horizontal velocity. But I need to find the time in order to get it. So we're going to solve for time first using our vertical data. And then once we find the time, we can solve for his velocity horizontally. So the time, I have VI, A, and delta Y. I'm going to use this equation. Delta Y equals VIT plus 1/2 AT squared. And if I substitute in, my delta Y is negative 1.8. My VI is 0, therefore VIT is 0. And I'm adding 0, so I'm not going to bother even writing that. I'm just going to write this, 1/2 times negative 9.8 times t squared. Okay, from here, half of negative 9.8 is negative 4.9, and I'm going to divide by that. So I'm going to do negative 1.8 divided by negative 4.9, which of course those negatives cancel. I get this, but this is t squared. Take the square root, and t is 0.61 if you round it. So that would be my time. Again, we don't need the time though, we need the velocity. He's driving at a constant speed, so I can use that constant velocity equation, delta x equals velocity times time. Again, delta x is 13.3, velocity is what I'm trying to find, the time is 0.61. You end up doing velocity is displacement over time, 13.3 divided by this answer. 13.3 divided by this number is 21.9, which is answer choice C for number 10. Does anybody have a question about number 10? Let's see how you guys did on number 10. My last class did pretty good on it. I don't think y'all did as good as they did, but about 2/3 of you got it right. Okay, so about a third of you missed it. All right, number 11. Number 11 says, a 0.5 kilogram football is kicked at an angle of 35 degrees with a momentum of 16 kilogram meters per second over level ground. Find its max height. So, I'm going to start by drawing a picture. I think that's always a good place to start. I'm going to recommend you do something similar. And so I have this football being kicked at this angle over level ground. I know it's going to have some trajectory that looks something like this. I know the angle is 35 degrees. Okay, and I don't know the velocity. Okay, instead they gave me a momentum. But I do know momentum is mass times velocity. And they didn't just give me a momentum, they also gave me a mass. So before I can do anything else, I first have one extra little step that I have to do at the beginning. I need to take my momentum, 16, and I need to figure out what the velocity is, because I can't use the momentum in my calculation. I need a velocity. The mass is 0.5 kilograms. It's already in kilograms. I don't have to do a conversion, so I can solve for the velocity like this. Pretty easy first step, but if you didn't do it, obviously you're going to run into problems. Okay, so if I divide both sides by a half or multiply by 2 effectively, then I know that my initial velocity is 32 meters per second. That velocity is at an angle. It says so in the question. It's kicked at an angle with this momentum. This momentum's at an angle, so is the velocity. So it goes right here, 32 meters per second. Okay, now I have a problem that looks like every other problem that we've been solving, and now I can set it up in the same way. But you do have one extra little step at the beginning. So if they give you a momentum, use that momentum equation and the mass to figure out what the velocity is. Okay, so let's go ahead and make a table. We need to organize our data, x, y. We need VI, VF, A, T, and delta x or delta y. All right, so I can't put this 32 in my table, because this 32 is at an angle. It is not a vertical velocity. It is not a horizontal velocity. It is a velocity at an angle. And so I need to first figure out how much of this velocity is horizontal, how much of this velocity is vertical. So I have to do some trig. I have to do SOHCAHTOA to solve for the x and the y component. The x component is adjacent to my angle, so I'm going to be using cosine to find it. The y component is opposite my angle, so I'm going to be using sine to find it. Okay, so let's go ahead and do that. I would say for my x component, I'm going to do 32, which is my hypotenuse, times cosine of 35 degrees. And I'm going to get this for my x component, 26.21. And again, in the x direction, my velocity remains constant the whole time because there is no acceleration. Now let's find the y component. I'm going to use sine. 32, that's my hypotenuse, times sine of my angle 35 degrees, gives me 18.35 as my y component. If you have something launched at an angle, use sine and cosine, use trig, SOHCAHTOA, to find the components. That's what goes here. Don't write 32 in here. All right, so now we have both of our components, x and y. Let's go ahead and see what else we can fill in. This particular question is asking us ultimately to solve for the max height. Okay, so when I start labeling some things, I've already labeled my horizontal, but for my vertical, remember we could do the vertical data for the whole thing until it lands, or we could do the vertical data just to max height, which is what I'm going to do because that's what the question's asking for. Okay, if you want to add an extra column and also do to landing, you can, but you don't need it. For this question, all I need to do is think about this point up here. Okay, at max height. So, at max height, my vertical velocity will be 0. I can fill that in. Okay, at max height, or rather the whole way, my acceleration is going to be negative 9.8 meters per second squared. Okay, and I'm trying to find my displacement at max height, because my displacement at max height will of course be the height that it's at. My displacement will be that height. So I'm trying to solve for this. Now, could I find time first and then do it? Sure. I don't need to though. I have an equation that I can use that has VI, VF, A, and delta Y in it, and it's this one. VF squared equals VI squared plus 2 times A times delta Y. I don't have to find time. You can, you just don't need it. So let's substitute in here. VF squared will be 0 squared, which is 0. VI squared is 18.35 squared plus 2 times negative 9.8 times delta Y. Let's go ahead and square this 18.35 that we had in our question. I'm going to square the unrounded one that's in my calculator screen, and then I'm going to subtract it to the other side so that I can get it over here. So that's going to be negative 336.9 equals 2 times negative 9.8 is negative 19.6 times delta Y. Okay, from here we're going to divide both sides by negative 19.6 to isolate our variable, and those negatives are going to cancel, so I just need to divide this by 19.6, and that's my answer. 17.2. Let's take a look. That's answer choice B, 17.2 meters. That will be my max height. Are there any questions about number 11? Again, about 60% of you got this one right, so some of you had trouble with it. Okay, I don't know if it was doing this first little step to get the velocity, if you forgot to get the components, or if you forgot to solve for max height. Okay, do keep in mind, if I had filled out this whole table and I found a time here, this would only be half the total time. I would have to double it before I put it on this side. Okay, just a heads up, just in case we have to do that. Okay, because I'm only finding half of the trajectory at that point. Okay, we didn't do that, but just in case. All right, number 12. Number 12 says, a cannon is shot with a velocity of 470 meters per second at 50 degrees. How far will the cannonball travel horizontally? Again, I'm going to draw a picture to get us started. There's my velocity. There's my trajectory. We're trying to figure out where it's going to land, how far away it will be. This is 470 meters per second, and they gave us an angle of 50 degrees. All right, so that's what I have for this question. Again, start with a picture. Make sure you know what you're solving for. I, in this question, am looking for delta x, my horizontal range. Again, I need to help organize my data, so let me go ahead and make a t-chart to keep my x and my y data separate. I'm going to want to be labeling VI, VF, A, T, and delta x or delta y. And again, I can't put 470 in this table because 470 is not my velocity horizontally, and it's not my velocity vertically, it's my total velocity. I need to find the components. So if this is my 470, I need the x and y components, and I have my angle. So again, you're going to go back to SOHCAHTOA. For this one, since it's adjacent, we're going to use cosine. So I'm going to say that 470 times cosine of 50 degrees is going to give me my horizontal component, which is 302.11. Horizontally, my velocity will remain constant the entire time because there's no acceleration. So I can fill that in like that. Vertically, I'm going to use sine because this is opposite my angle. So I'm going to say 470 times sine of 50 degrees. And I get this, 360.04. That is my initial vertical velocity. All right, so again, if you have it at an angle, find the components. Okay, that's all the information that's given in the question, but that's not all the information I know. Again, when I'm solving these, I can, this is all I know horizontally, but vertically, I know some stuff about this point, and I know some stuff about this point. In this particular question, I want to know how far it will travel horizontally. I want the whole thing. So last time I found data here just to max height. This time, I'm not going to do my data just to max height. I'm going to do my data all the way to impact. And at impact, I know my final velocity. If my initial is 360.04, my final will be negative 360.04. I also know that my vertical displacement will be 0 because I'm going to land at the same height from which I launched. I know also that my acceleration is negative 9.8 meters per second squared because it's due to gravity. So from here, if I want to find range, which is here, I first need to get time, and I have plenty of information over here to do it. So I'm going to use this equation. VF equals VI plus A times T. VF is negative 360.04. VI is positive 360.04 equals negative 9.8 times time. Not equals, plus, sorry. Okay, so I'm going to subtract this from both sides. And then divide by 9.8. The negatives are going to cancel, and that's my time. Okay, 73.5 effectively would be my time. I rounded that. And now we can find displacement horizontally. Again, horizontally my acceleration is 0. I have this equation. Displacement is velocity times time. So I'm just going to take this time, I'm going to multiply it by my horizontal velocity, 302.11, and I get a horizontal displacement of 22,198, which is answer choice B.
Good morning, please pardon this interruption. Teachers, if you have students that have...
All right, so again, does anybody have a question about number 12? Okay. Let's go ahead and turn the page and look at number 13. Number 13 says, in projectile motion, the vertical component of the velocity. And when we talk about vertical component of the velocity with a projectile, we will have vertical acceleration because we have a vertical force. We have gravity acting on this. And so we're not going to say velocity is constant because I know it's not. We're not going to say that it's 0 because it's not. At the top of its path, your vertical component's not at a maximum, instead it's at a minimum. So the only choice left is D. It changes by negative 9.8 meters per second each second. That is your vertical acceleration. That's gravity right there, your gravitational acceleration. And almost all of you got that right. There were a couple people that missed it. Okay, so I don't know if you misread it and thought it said horizontal or what happened, but the only answer to number 13 that makes any sense is D. All right, this is for the next 3 questions. So again, if you don't have Form A, you can look for this for numbers 14, 15, and 16. Number 14 says, in which direction does the acceleration vector point at point A? Okay, at point A, you have, well, at all these points actually, you have acceleration due to gravity, and that's it. The only force acting on a projectile is gravity. Therefore, your acceleration will be in the same direction as that net force. It's down at point A. It's still down at point B. It's still down at point C, which, by the way, is number 16. So both number 14 and number 16 should be B down, okay, because it's the same everywhere acceleration is. Okay, but number 15, which is in the middle of on mine, yours again might be in a different order, but number 15, some of you missed. In fact, almost half of you missed it. So this was one of the most missed questions as well, and I'm not sure exactly what happened, but it says, in which direction does the velocity vector point at B? I take that back. I know exactly what happened. You put D if you got it wrong. If you got it wrong, you told me that peak height implies velocity is 0. And while that is true for your vertical velocity, you still have forward motion. Again, my horizontal velocity is constant at every point. If it's 2 meters per second, it's 2 meters per second everywhere, including at point B. So you do have a velocity vector at max height if your projectile is moving forward. Your velocity vector would be forward. If it was thrown straight up in the air, then D would be correct, because peak height does imply 0 vertical velocity. If you didn't have any horizontal component, you could pick D. But with the way this question is worded, and with the drawing very obviously moving forward, the answer that you should have selected for number 15 is C. And as I said, almost half of you put D. Okay, so don't get thrown off. Okay, it is still moving, it's just not moving up or down. Vertically it stops, but horizontally it continues moving forward. Are there any questions about numbers 14, 15, or 16? All right, we are almost done. Let's look at 17 and 18, which go with these graphs. And guys, if you're not too fond of graphs, then definitely listen up, because you will have graphs on your test. They will be there. Okay, so this one says, use the following graphs to answer the next 2 questions. The following 5 graphs represent position versus time graphs for 5 different objects. Number 17 on mine says, assuming these are position time graphs, which it said already, which graph shows the position time data for the horizontal motion of a projectile launched forward? Okay, and if I'm trying to look at horizontal motion, I need constant velocity. Horizontally, I have constant velocity. We've been writing it in our table the whole time. Acceleration is 0. My velocities stay the same. We've talked about it several times already. On a position time graph, if you want to show constant velocity, you need to have a straight line. If it's moving forward, that straight line needs to have a positive slope. And so it says it's launched forward, therefore we need a positive slope. That's going to be answer choice B for number 17. Okay, so 17 should be B, and again, only about 2/3 of you got this right. Okay, so if you missed it, ask a question if you still don't understand what I'm saying, or make a note. Okay, but if you're trying to show constant velocity on a position time graph, you need a positive slope, because it's forward, and a straight line. Okay, and the only one that has that is B. Number 18. Assuming the graphs are position time graphs, which graph shows the position time data for the vertical motion of a projectile launched forward? And again, for my projectiles, vertically, I need acceleration. And that means a curve. On a position time graph, acceleration means that I need to see a curve. And there are only 2 graphs up here with a curve, A and D. It's got to be one of those 2. Okay, but let's see which one makes sense. A shows an object that vertically is moving upward, slows down to a stop, turns around, and then moves downward and speeds up. D, on the other hand, shows an object moving downward, slows down to a stop, and then starts moving upward and speeds up, which does not make sense for a projectile. They don't move down and then turn around and move up. That would make sense if I was like bouncing a ball, I guess, on the ground, but not for a projectile. The answer that you need to select for number 18 is A. Okay, and again, like I said, only about 2/3 of you got that one right. On your test, graphs are fair game. These are position time graphs, but I could just as easily ask you about a velocity time graph. We took notes on it. Go back and look at the graphs in your notes. Make sure you know what your velocity time graphs look like as well, because this is position time. We just went over that, so check the others also, because you could see it on your test. You will see graphs on your test, and they may not be these. They might. You should know these too, but they may be velocity times, so make sure you know what both of those look like. Okay. Again, I already mentioned this, but in addition to the stuff in this quiz, there were some questions that I would recommend that you look at. And so I was going to go ahead and talk about those as well while we're sitting here. And the first one was number 5 on 705, the review, and then on 702.3, 14, 16, and 17. So let me go ahead and do that. So I have the review opened, 705, and I'm going to scroll down to number 5, which says, a projectile is fired at an angle of 67 degrees and travels a horizontal distance of 13 meters on Earth. Which of the following changes will result in it traveling a greater horizontal distance? And it wasn't really specifically covered in your quiz about the 45 degrees versus the other angles, so I wanted to just really quickly remind you. But you're going to get the greatest horizontal distance if you have a launch of 45 degrees, period. And if it's equidistant from 45, then you'll have the same exact range. Now, going larger than 67 to 75 is going to make it a shorter range. It's going to have more air time, but the range will be shorter. Okay, so this smaller angle of 23 is actually the same number of degrees away from 45 as 67. It would have the same range. So the only angle here that is actually greater is 45. Slower launch velocity, not going to help my range. Okay, that will make it shorter. Faster, on the other hand, I could pick. And then smaller gravitational field strength, that would actually give me a greater range. So again, there are different factors that we talked about. I already mentioned them on the quiz, it just wasn't specifically asked there. Okay, now if it had said airtime, then yeah, that bigger angle would be great. Okay, but not for what it says here. So on this one, it's only these two. These are randomized. You may or may not have the same values on yours. The other questions that I suggested you look at were on this assignment, 702.3 mixed projectile problem set, starting with number 14. So I'm going to scroll all the way down to 14, which is this one. It says, 2 balls roll horizontally off the edge of a 1.54 meter tall table. Ball A has a mass of 2 kilograms and is moving at 1.6 meters per second. Ball B has a mass of 4.9 kilograms and is moving at 8 meters per second. Both of the balls leave the table at the same instant. Which hits the ground first? Okay, so again, horizontal motion is independent of vertical motion. Their speeds don't matter. If they're horizontal, it doesn't affect the air time. Neither do their masses. So I would expect these two, because they're leaving from the same height, to hit the ground at the same time, even though they have different sizes and even though they have different speeds, because those speeds are horizontal. Now, if one of them was launched up at an angle and the other was horizontal, that's different. If you're launched up at an angle, yeah, that's going to affect your air time. Or if it's thrown down, that's going to make it hit the ground faster. So if you have an upward or downward component, yeah, that's different. You might have to calculate it with all these different numbers. But if they're both horizontal, then you would expect them to hit the ground first if they come from the same height and they leave the table at the same time. There are some calculations here as well, which I'm not going to do, but you're welcome to look at those too. I mostly just wanted to talk about the concept question here. Number 16 says, Snoopy is testing physics at the top of his doghouse with the help of 2 friends. Together they throw 3 balls at the exact same time from the exact same height. One is thrown straight up, one is thrown horizontally at the same speed, and the third is dropped from rest. What order do they hit the ground? And I just kind of talked about this as well. That's why I'm going over these, because I'm telling you concepts like this are going to be on there. Okay, if you throw it straight up in the air, it's going to have more air time than throwing it horizontally, because you're throwing it up. You're giving it some additional height. Okay, and so the one that's thrown upward would hit the ground last. But the one that's thrown horizontally and the one that's dropped would hit the ground at the same time. Now, these are random, so I think some of these actually say there's a ball thrown down. That would hit first. If you throw it down, it's going to hit first. And then your dropped and horizontal would hit at the same time, and then you're up. Okay, the one thrown up. So the order that I would pick here is that dropped and horizontal tie for first place, thrown up lands last, based on mine. But again, if it was thrown down, if that's a choice, and again, since it's random, it might be on yours, then you would say that that hits first, because you'd have an initial downward velocity. All right, but that is 16, and the last one is 17. And guys, I would very strongly encourage you to listen up while I talk about this, because you need to know how to handle this. It says, a slingshot does 12.2 joules of work to move a 310 gram rock from rest when it's launched horizontally off a cliff. This has a little step we have to do before we can do any of our projectile math, just like the one in the quiz, but the one in the quiz had momentum. I could just as easily throw work at you and have you do the same thing. Guys, if you do work to move something from rest, work is equal to change in kinetic energy. Since it's from rest, the work I do, that 12.2 joules, that is the kinetic energy afterward. Okay, so if you wanted to actually answer this question, okay, we would need to use the kinetic energy equation. Sorry, I have like so many windows open. Let me do this so we can actually work it out, if I can get it to stay. All right, so if we wanted to do this, we would, trying to get this thing to, there we go. It does not like me today. There, okay. Try to work it out real quick. So, if we're doing work, again, after you do work to move something from rest, your work equals your change in kinetic energy, and since it had 0 to begin with, it will give you your final kinetic energy, which means my kinetic energy of my rock after launch is 12.2 joules. That is its KE. So I can now take this number and I can use the KE equation and set it equal to 1/2 mv squared. Okay, so again, you have to be able to do this little step. You're going to see it again. I'm telling you, you will see it. Okay, so if I want to do this, again, my masses do need to be in kilograms rather. This is in grams. So I do need to convert 310 to kilograms, which means I need to divide by 1,000. So when I plug it in, I'm going to say 12.2 joules, which is my KE, equals 1/2. My mass, instead of being 310, is 0.31. I divide it by 1,000 times v squared. Okay, and so we're just trying to, we got to get half of that number, so let's just divide that by 2, and we have this. 12.2 equals 0.155 v squared. We're going to divide both sides by 0.155. And let's go ahead and divide that on my calculator. 12.2 divided by my answer. And I get that v squared is equal to 78.71, but I need the square root of it. V equals 8.87. These are rounded. But this is now my initial velocity. So I had to do that step before I could do the rest of the calculation. You will have to do that. Okay? I'm telling you, it will be there. Okay, so make sure you know how to do that. Now this velocity, if the question had said it was at an angle, I would draw it at an angle, but the question says it's horizontal. So this becomes my initial horizontal velocity in this question, and then you solve it like normal. But you have this extra step first. Okay, so be able to do that. And again, if it had said that you do this much work to launch it at an angle of 30 degrees, well then put it at an angle of 30 degrees after you solve for it. Okay, but you need to be able to use the kinetic energy equation to find the velocity. Does anybody have a question about this one? I would strongly encourage you to go back into this assignment. This is number 17, and I would encourage you to try it. Make sure that you know how to do it so that you are going to be able to get full credit on that question. 702.3, number 17. Okay, again, look over the quiz, look over your myOpenMath, look at your unit summary. You've got a lot of resources. And if you still have questions, please come after school for tutorials so that we can get those answered.